So what I want to talk about in terms of our waste to energy project is the difference between energy and power. But before we do that, need to define something called work in technical scientific terms. So work is just the term that's used to describe what's going on when an object is moved over a given distance against an applied force. So the equation to calculate is just work equals the force applied times the distance applied over. This can be any type of force, like gravitational force, for example. If you lift an object with a certain mass upwards against gravity, you're applying force over that distance that you lifted upwards. So that's one example of work. If you compress a spring, the spring exerts force as you compress it, a resisting force. And whatever distance you compress the spring, you're applying the force over that distance. Use that to calculate work. If you take two of the same similarly charged electrostatic particles, like two positively charged particles, you move them towards each other, there's a resistive force, and the amount of distance you push the particle, against that force, that will be represented as work also. All right, so there's all these types of physical work, or I should say work that's associated with physical forces, movement against them, and that's going to be tied to energy. Right, so just looking at the units, all right, if we use metric units, force is in newtons, the distance is in meters, so it's a Newton meter, which is equivalent to kilogram meter squared per second squared. Talking about imperial units, it's foot pounds, foot pound force, foot pounds of force, I don't know, foot pounds, I guess. So pound is the force unit, foot is the distance. Okay, so if work is what goes on when you're moving something a given distance, a specific distance over against a force, energy can be described as the capacity of matter to perform work. Right, so however much energy something has, it's tied into how much work can be done, whether it's a substance or an object. And if work is performed by the object or substance, then it loses energy. Energy is transferred from it to perform the work. If work is performed on the object or substance, like you compress it with an external force, energy is transferred into it. Energy goes into the object. And so almost think of energy as being like a bank account. The amount of funds in somebody's account for matter is it's a measure of how much work can be performed by that object or that substance. The more energy it contains, the more work it can perform. And the scientific unit, the International System Unit for energy, is a joule, which is equivalent to that Newton meter, right? So, force of 1 Newton applied over a meter, it's 1 Newton meter, 1 kilogram meter squared per second squared. That's defined as a joule, right? So the joule is the unit that's used in science for work and energy. There's some different units we can use, as we're going to see. Some are specific to heat. All right, you've probably seen these, before, familiar with these. A calorie, in terms of heat, it's a heat unit. A unit of heat energy is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade. A British thermal unit, a BTU, it's also a heat unit defined as the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So using the imperial units. And these are convertible to those other types of energy units we just talked about, whether it's joules, scientific metric units, or imperial units, foot pounds. 1 calorie is equal to 4.184 joules. 1 BTU is equal to 1,054.35 joules, roughly, depending how you define things. In terms of that imperial unit, about foot pounds, 1 calorie of heat energy is equivalent to 3.086 foot pounds of work or energy in those units. 1 BTU is equal to 777.49 foot pounds. So the point is, there's different units to talk about the same thing, about energy, right? Depending on the context and which system of units you're using. Just to give an example, right? Let's look at the energy content of fuels. So when they talk about a fuel and they mention its energy content, it's also referred to as its energy density. That's just a measure of how much energy is stored in the fuel. Can be defined in how much heat would be released when you combust a given amount of the fuel. So for example, anthracite coal, the energy content given for it is 34.6 megajoules per kilogram. So it's using those joule units. Mega just is a prefix for a million, the metric prefix for a million. So 34.6 million joules, 34.6 megajoules. That's how much heat is released when you combust 1 kilogram of coal. It's anthracite coal. So, if you combust the 1 kilogram of coal, releases 34.6 megajoules, 34,600,000 joules. That's also equivalent to 32,816 BTU, or 8,269,598 calories. Right. So you can just see that, these energy units, again, they're convertible, right? They're all talking about energy. We're talking about megajoules, kilojoules, joules, BTU or calories. These are all energy units. Sticking with this energy content of fuel example, the energy content of coal and other fuels is oftentimes given in units of BTU per pound or even BTU per ton. Let's look at this. For the same coal in these different units has an energy content of 14,875 BTU per pound. That means if you combust a pound of coal, the heat release is 14,875 BTU. That's equivalent to 15,683,461 joules, 15.683461 megajoules, or 3,748,437 calories. And if we want to convert that pound to kilograms, they would turn out to be the same amounts of energy that we talked about before in the megajoules per kilogram. So, without worrying about getting lost in these numbers, it's just showing that energy, is one thing. This ability to do work, the amount of stored energy, the amount of energy stored in something that can do work later. That's all given in these units. Joules, kilojoules, megajoules, BTU or calories. And this is a summary, all right? So scientific metric, imperial. I didn't really talk too much about foot pounds. That's not used very much. You can, but it's usually going to talk about in joules or these heat units, BTUs and calories, and they're completely interconvertible. It's like different types of currency, right? You can convert between various currencies, where you're still talking about the same amount of funds. This one, 1 joule is equal to 0.7376 foot pounds. It's also equal to 0.0009445 BTU, 0.2390 calories. Right. So this is just types of energy units that are thrown around. We're going to see another one soon, but we have to talk about power first. So power is not the same thing as energy, right? Power is the rate at which energy is produced or consumed. So over per given unit of time, how much energy is produced by some kind of energy generator or consumed by some kind of energy demand. So in these scientific metric units, our base unit of power is a watt, abbreviated with big W. 1 watt is equal to 1 joule of energy per second. So you see the power units always have to have units of energy per second, and that's why they're different than energy. Energy is something like a joule. Power is joule per second, and they call that a watt. And some things that are more familiar, because they're bigger units that we use for like utilities, power, appliances using power and stuff. 1 kilowatt versus just 1,000 watts, and 1 megawatt is 1,000,000 watts. Right? So these are terms that we're going to see for our project. If we talk about imperial units, right, the imperial unit for power is a horsepower. So like in the old days, trying to figure out how much, if a standard pony in the mines could lift a certain amount of pounds of, so something of coal or iron ore up a certain amount of feet, they tried to normalize this. So 1 horsepower is equal to 33,000 foot-pounds per minute. That's the rate at which the energy would be produced or consumed by something in horsepower in these imperial units. If we're talking about heat, they just use BTU per hour, nothing special, right? It's just like how much heat is given off, it's BTU per hour. They could do calorie per minute, calorie per second, but it's not too common. You'll see BTU per hour sometimes for the rate at which heat is released, produced, or consumed and absorbed. And when we're talking about electrical power, meaning the rate at which electrical energy is produced or consumed, it's usually reported in watts or units derived by watts. And this is the important part, right? Not to get confused or not to conflate units for electrical power and units for electrical energy or electricity. Right? So power is going to be watts or kilowatts, megawatts, something like that. And remember, it's energy per unit time. For example, a 500 kilowatt diesel generator is going to produce, 500 power at a rate of 5,000 kilowatts. That's I'm sorry, 500 kilowatts. That's 500,000 watts, which is 500,000 joules per second. So again, kilowatts is a power rating. That's energy per time, equal to 500,000 joules per second, or 500,000 kilowatts. And then if you want to look at how much energy, electrical energy, is going to be produced by this generator if it's operating for an hour per hour, you just do the 500 kilowatts, 500,000 watts, 500,000 joules per second, times the amount of seconds in an hour. So 60 seconds per minute, 60 minutes per hour. That'd come out to 1,800,000,000 joules, which is 1.8 gigajoules. Giga is a prefix for billion, so 1.8 billion joules. If you had a load, an electrical load, a demand. So if you had a 35 horsepower electrical motor, which is equivalent to 26.11 kilowatts, it's consuming electricity at that rate. It consumes 26.11 kilowatts, which is 26,110 watts, which means it's consuming electrical energy at a rate of 26,110 joules per second. You can do the same kind of thing per hour. 1 hour times that 26.11 kilowatts, or 26,110 watts, joules per second, times the amount of seconds in an hour, 60 seconds per minute, 60 minutes per hour, you'd get 93,996,000 joules, or 93.996 megajoules. Megas for a million. All right. So again, these examples just showing that, you know, the rate at which power is generated or consumed is one thing. That's kilowatts, megawatts. It's like joules per second, amount of energy per second. And you can calculate that for any amount of time. You know, if this generator is operating for an hour, 24 hours, 6 months, whatever it is, you can do the calculation of how much actual energy will be produced over that amount of time at that rate. You know, it's something similar to, like, if your car goes 60 miles an hour, how far are you going to go in 1 hour, 10 minutes, 24 hours driving at that rate? You know, it's the rate versus the amount that's produced over a given time. Okay, and this brings us to a commonly used unit for energy. So another unit for energy, specifically for electrical energy, is something called a kilowatt hour, kWh. And this is where the confusion, it's really easy to get confused, right? We talked about kilowatt, which is a power unit for the rate that electricity is produced or consumed. So kilowatt hour is actually an energy unit, because it's like if you take the kilowatt, if you take something like, for example, 1 kilowatt, right? If something is producing or consuming electrical energy at a rate of 1 kilowatt, we said that's 1 joule per second. But then if you multiply that by an hour to figure out over how much energy is produced or consumed over an hour, and you have to, take into account of how many seconds there are per hour, it comes out like this. So that 1 kilowatt generator is producing 1,000 joules per second, 1,000 joules of energy per second. So over 1 hour, where there's 60 seconds per minute, 60 minutes per hour, 3,600 seconds per hour, we multiply that by 1,000, and we get 3,600,000 joules, or 3.6 millijoules, right? And that's equivalent to a kilowatt hour, right? So if you have a 1 kilowatt generator operating over an hour, since kilowatt is the rate at which the electrical energy is being produced in terms of joules per second, we do the unit conversion, for amount of seconds an hour. The amount of energy produced by that 1 kilowatt generator in an hour is 3,600,000 joules, which is equivalent to 1 kilowatt hour. This is the part to be real careful about, right? Kilowatt hour, the way we define this, is a unit of energy. It's a bulk amount of how much energy is produced over a given amount of time. Kilowatts is just the rate at which the power is produced. So the kilowatt, it doesn't matter you don't need to know how many hours the generator is running for kilowatts. That's just its rate. However long it's running for, 1 second, 1 hour, 1 year, it's going to produce energy, the rate of 1 kilowatt, 1,000 joules per second. But kilowatt hours, again, is how much energy is produced by that 1 kilowatt generator per hour, and it could be equated back to joules. So kilowatt hours is another energy unit, whereas kilowatts is a power unit. And those are the ones that's important not to get confused. So talk about an example just relative to the biogas portion of the phase 1 of the project we're talking about. Okay, so if those 2 gas digesters, or biomass digesters, produce enough biogas to fuel that 1 megawatt generator, the engine, if the engine has a rating of 1 megawatt, when it's operating, it's producing 1 million watts, so 1 million joules of electricity per second. We want to do that in terms of how much per hour. 1 million joules per second times 60 seconds per minute times 60 minutes per hour is 3,600,000,000 joules, or 3.6 gigajoules of electricity produced per hour. Again, the difference between power, the rate that the electricity is produced at, and the total amount of electricity produced per given amount of time, whether it's a second or an hour. But it's going to be simpler in this kind of thing. If we want to use those units like kilowatt hours, or this time I'm going to use megawatt hours. Since we're talking about a megawatt, 1 megawatt generator operating for an hour is just going to produce 1 megawatt hour of electricity. Megawatt is the power rate, the electrical generation rate. Megawatt hour is the amount of electrical energy produced. 1 megawatt hour is equal to 1,000 kilowatt hours. Both of those are equal to 3.6 gigajoules, or 3.6 billion joules. And these are all energy units, right? Even though they have megawatt and kilowatt in them, and you make it megawatt hour and kilowatt hour, now it's talking about energy, not the rate that energy is produced, the power. Okay. So again, megawatt hour is a unit of energy, whereas megawatt is the rating of our system, means that's the power, it's a unit of power. It's how much energy is going to be produced by our system per unit of time. And megawatts means, millions of joules per second. But then when you operate over a certain time, we can talk about the total amount of energy in megawatt hours, kilowatt hours, joules, whatever we want. And here's where kind of the bottom line comes in. All right. Some of these calculations are going to be easier using units like megawatt hours or kilowatt hours, and electricity usually bought and sold, by the utilities, by customers in terms of kilowatt hours. So we're going to want to use these type of units. See what this pencils out to for the biogas project. Right. For example, let's assume that we have that 1 megawatt biogas energy facility operating, and we're going to assume, it's online 85% of the time, taking into account planned maintenance, unplanned maintenance, an uptime of 85%. So if we want to calculate the amount of electrical energy produced by this facility over 1 year, we're going to take just 85% for the, of the electricity that produced if it's running continuously for a year, but we're going to get 85% of that. And the amount of energy that would be produced per year, the amount of electrical energy, okay, we take that rate, our power rating, 1 megawatt, that's 1,000,000 joules per second. But if we want to do it in terms of these megawatt hours, all right, we're going to, it's 1 megawatt hour in an hour, of course, and in a year, there's 8,760 hours per year. You multiply that, we get that in 1 year, 85% uptime, the amount of electrical energy that would be produced is 7,446 megawatt hours, which is the same as 7,446,000 kilowatt hours. We could convert that to joules if we wanted to, but there's really no need to, because according to that tariff, according to the PPA, the electrical tariff paid is going to be 2.82 baht per kilowatt hour. And you can make that in however many baht per joules if you wanted, or per kilojoule, per megajoule, but that's not how they do it. Usually it's per kilowatt hour. So since our facility would produce 7,446,000 kilowatt hours over a year, operating 85% of the time, you multiply that by 2.82 baht per kilowatt hour, that would give us a total of 20,997,720 baht per year. All right, so hopefully this makes it clear what the difference is between power unit. Well, just what the difference is between power and energy to begin with. One's a rate. Power is a rate which energy is produced or consumed, and these kind of units. All right, so we talked about joules, BTUs, and all that stuff. They're equivalent, but the main ones we're talking about electricity are going to be things like megawatts for the power rating, and megawatt hours is the actual amount of energy produced, per hour of operation. And then depending on how long of a period you're looking at, per day, per week, per month, per year, you can calculate the total amount of energy that's going to be produced by your facility with a given power rating, the rate at which energy is produced in terms of megawatts.